Hello, everyone. Welcome to this morning's session. My name's David.
I'm Susannah.
We're both engineers working on the Maps API in the Sydney office. And today, we're going to be talking to you about Speedy maps. So in particular, we're really going to be emphasizing how you can make your website itself as quick as possible. And then once your website's quick, how you can get the map on that page to be super fast as well.
So over the years at Google, we've learned a number of things. One of the most important being that fast is better than slow. And this applies directly to loading web pages fast and making them fast once your users arrive at the web page. Why is this important? The longer it takes your web page to load, the more likely your user is to go and find what they're looking for somewhere else. And it's important that once they arrive at your website, that it performs well and interacts smoothly and seamlessly for them so that they forget that they're in this two-dimensional web browser with this what could be static content, and instead immerse them in the world that you're trying to deliver. So today we'll talk about how to make both of these parts of your page faster. On the Maps API team, we work really hard to do our part to make sure that what we're delivering to you is fast, but it's important that you also use these principles to make your page and your map fast. So we'll talk about when you load resources, how to optimize them and make the resource loading as efficient as possible. We'll also talk about some of the difficulties of developing in the browser and how you can work with and around it. Then we'll talk about how to move some of the hard work out of the client and onto your servers and our servers. And we'll cover some of the tools and technologies that exist in the browser to help you make these pages as fast as possible. So here we see a chart that shows the amount of time it took to load various sized JavaScript files. Now, loading resources is a combination of things. It takes time to do a DNS lookup, to make a return trip to the server to actually fetch the data, and then to parse the data and to execute it in the browser. Now, these numbers are pretty general. Because there are these different components to loading, and every browser is a little different, and every device is different, there's no hard and fast rule as to how long it takes to load a particular resource. Plus, that parsing and executing can vary a lot by the complexity of the resource loaded. But what we do know is that the bigger the file is, the longer it takes. So this chart is just emphasizing that point. Bigger files, longer time. Now, there are many ways to reduce the size of the files that you download, but the really core principle here is to load only the necessary resources at any given time. That because it takes time to load each resource and each big resource, load as little as possible. We do this in the Maps API by only loading up front what you need to create your map, and we wait to load the rest of the components later until they're actually required.
So one of the most powerful ways you can reduce one of the heavy components of your page, the JavaScript, is to send it through a compiler or a minifier. So the job of a minifier is basically to do some simple manipulation of your JavaScript files. For example, it will strip out comments, it will collapse white space so it's all normalized, and it can also do some simple variable renaming, particularly the parameters of functions. JavaScript compilation really takes it that next step because it can understand the semantics of what your JavaScript is trying to do. And so it can do much more aggressive optimizations, like renaming variables that look like they're global, but only your program's using them, and even doing things like inlining functions completely away. So in the top code sample there, I've got a bit of a toy piece of code which calculates the nth Fibonacci number. And as you can see, I haven't taken any care making that small. There's big variable names. I've even made a bit of a silly function just to add two numbers together. So you can see it's a big waste of space. Now, when I ran that piece of code through the open source closure compiler, you can see the same functional piece of code at the bottom. It's much, much more terse. It fits on a single line. And you can even see that it's taken away some of those extraneous function calls that I've made. And it's really, I don't think you could write that any more succinctly. So why would you run your code through a compiler or a minifier? Well, the obvious answer is that it's smaller. As you just saw, many lines of code with large variable names, it became very small. So this really helps in the download component, so the files themselves are much smaller. The second advantage, and this really applies more to the compiler than to the minifier, is that it can make your code itself simpler. It can, if you've got a mathematical expression, it might be able to pre-calculate that at compilation time, and it can inline functions away. So the code itself can become simpler, which can speed up the parsing and the execution on the page. And I think one of the most important reasons that you'd want to use a compiler is that it actually can make your JavaScript maintainable. Because you're not worried about the code that you're actually writing is going to be sent to the end user, you can be very clear in your code. You can write large comments, you can use very descriptive variable names, and you don't have to worry about all those little extra bytes that have been sent down to the client every time. The Clojure compiler also has another really powerful tool which helps keep your JavaScript maintainable, and that's that it provides typing to JavaScript. So you can do things like define object types, define interfaces, and the compiler can catch little errors you're making, like typos or wrong number of arguments to a function call at the compilation time. So you can get your answers straight away rather than after 20 minutes of digging through stack traces. The open source Clojure compiler actually forms the basis of how we, as the API team, compile all our code. And there is an external file available in the SVN repository which lets you compile your own web application against our API. Just to give you a little feeling for how powerful these minifiers and compilers are, here are two real-world examples. The jQuery library, when you concatenate just the raw source files, is about 233 kilobytes. After minification, that drops down to 94 kilobytes. The Maps API itself weighs in at a massive 2.4 megabytes before we do any compilation of it. And you think that's an amazing amount of code, but that also includes a lot of commenting, a lot of documentation that we have in our code directly there because it makes it much more easy for us to work with it. After we've run it through a compiler, the whole API is reduced down to 336 kilobytes. So, that's in the order of 14% of the original size.
So though it's important to make each of your files as small as possible, it's also important to remember that each file counts when you download it. This is a waterfall chart from Firefox 3.0 where we're loading 13 different JavaScript files with a total of 730 kilobytes of data. And this took 4.5 seconds. Each of these is downloaded in sequence. Now, many browsers since Firefox 3.0 can actually load files in parallel, and this becomes much shorter time and much better. But we're still dealing with many old browsers out there and many mobile devices that have low CPU, low RAM, and low bandwidth often. And so the load time, it can't be as parallelized for these reasons. And so if we take these files and instead bundle them into two separate downloads, where we're still loading that same 730 kilobytes, we can get the time down to 1.8 seconds to load that same amount of data. So where possible, use multiple files for development, but then make sure to concatenate them before you serve them to your users so that those resources load quicker. These same principles apply to images. So with images, we can concatenate images by using what we call an image sprite. An image sprite is a collection of multiple individual images in one larger image that's loaded together, but then only shown in portions. So here we have, at the top, we see 3 different Pegman images. But there's actually, to show Pegman, because we show them at so many different angles as you drag them around the map, there are actually about 30 Pegmans. But they're all concatenated into one image, because usually we need all of these 30 Pegmans all together. So we load that one image, and then using HTML and CSS can show only the relevant Pegman. So here are some code snippets for doing it purely in HTML, and then another to show a CSS block for it. So when doing it in HTML, you specify a div that is the width and height of the image you actually want to show, so the size of the actual Pegman. You set its overflow to be hidden so that anything extending outside of that div is not shown. Then you put inside the div an image tag, whose source is the complete image sprite, so the full 30 pegmans. Then offset within that image, you set the left and top positions so to be the point in the image where that pegman starts, the top left corner of that pegman. So because this particular pegman that I'm showing on the slide is 98 pixels into the image, I set the left position to be minus 98 pixels. The CSS is very similar, except that you can use the background image property and the background position. Now, the downfall of using the div is it's harder to print images that are in divs with background images. It depends on the browser whether you can do that. Otherwise, it's a great way to go for rendering your image sprites.
So another way you can bundle your images together is to bundle them directly into the HTML itself rather than alongside other images. On this slide, I've got two blue markers. But the way that those two markers are being rendered by the browser, the way they've been delivered to the browser, is completely different. The top one is very much the traditional image that you probably all know and love. It's just an image tag which specifies where its source is. So when the browser encounters this tag, it needs to make a HTTP request to your server, go out, request the image from your server, bring it back, download it, decode it, and then display it on the page. With the second marker, I've actually included the data for the marker directly in the page itself, so there's no extra connection required. To do this, we use something known as data URLs. And with a data URL, you basically have to specify 4 different things. The first thing is that you start the URL with data instead of HTTP like you usually would. The next thing you need to do is tell the browser what MIME type it's supposed to be expecting so it knows how to decode the data when it sees it. And in this case, it's an image ping. The third thing you need to do is tell the browser how you're going to encode the data for it. And here, we've done base64 encoding, which is what you'll do 99.99% of the time. And lastly, you actually include directly in the URL the data of that image encoded in base64. So the actual binary data that describes that image. Using the same data URL techniques, it's equivalent to embed that image source directly into a JavaScript file or into a CSS file. So wherever it's most appropriate, you can use it. Now, why would you want to use this and why would you want to avoid it? The obvious advantage, as I already discussed, is that there's one less HTTP connection. So if you have a page with a small icon, the browser doesn't need to do any extra network work to get that image on the page for you. And also, it can be conceptually simpler than spriting. Because each image contains the data for a single part of your image, you don't have to worry about where your little image fits in the context of a much larger sprite and be worrying about offsets. You can deal with one image at a time. On the other hand, there is limited support for data URLs in older browsers. For example, Internet Explorer 7 has no support at all, and IE8 has limited support. On the other hand, to this point, all modern mobile browsers do support data URLs. So they're a really good candidate for data URLs, because in these devices, you do have really limited bandwidth. For example, in the Maps API, we actually use data URLs to deliver all the images required for our zoom controls, for example, in mobile devices. The other thing that's worth bearing in mind is that base64 encoding of the binary data can swell the image by about 1/3. Generally, if your server is set up to handle gzipping correctly, though, that overhead pretty much shrinks to nothing. And just briefly, just to show you that it's not a very difficult task to actually generate that base64 data, on the top code snippet, I've got 3 lines of Python which open up any image file, or any file really, and return what that base64 data looks like. The bottom one is actually a little bit more advanced, I guess, in that it's a PHP script which will generate the base64 encoding at runtime in the server, so you don't even have to worry about storing that base64 data anywhere. Now, the principles we've talked about for images apply just as strongly to JavaScript and CSS, and really any resource that you can make it apply, that you can use it with. So with JavaScript, as Susannah mentioned, keep those files together. If you can use a compiler to compile all your source code together, that's fantastic. And also only load the bare essentials into the head tag itself, because anything in that head tag can stop the body from rendering properly until all your script is downloaded, parsed, and run. So if you've got heavyweight things like things that deal with especially user interaction, try and load those later on in the page's lifetime. It's also useful to try and keep common scripts from infrequently used scripts. So if you use some parts of your library on every single page of your site, keep them in a separate file to those that you'd use only on 1 or 2 pages. Because that way, the user's always going to have that common page in their cache, and they won't have to re-download it for every page they visit. Again, apply these concepts to CSS as well. Bundle the files together, compile them, minify them if you can. And also, at all costs, avoid the @import tag. Because what that means is the browser has to go out, read one CSS file from your server, and only then does it know that it needs to go and start downloading a second one. So it can really significantly delay how long it takes to start.
Now, in developing the Maps API, we use all of the techniques that we've talked about so far. Delay loading code, compiling and minification, image spriting, embedding data URLs, and concatenating JavaScript to have fewer downloads. To walk you through exactly how the Maps API loads this, you, the developer, start here in the upper left-hand corner by loading the Maps API bootstrap, as we call it, so embedding the script tag on your page. This then loads a file that is the bare minimum it takes you to start developing your mapping application. So we load only the interfaces in what we call main.js. This is all the classes that you can instantiate. You, the developer, then create a new map, giving it the center, the zoom, its map type ID, at which point we do actually have a little bit of implementation in that first code just to make this part faster, which is to load a static map right away. At the same time, we go and we delay load all of the implementation for the actual functionality of the map. But here, when we have to load multiple files, we'll concatenate them. At that point, we then load the map tiles. So we're loading things as you need them, both compiled together as small as possible, but split out where appropriate. Now I'd like to talk a little bit more to drive home this point of how we do things about the new Maps API libraries feature. So over time, that interface file, that main.js, can grow and grow as we add more and more features. So to get around adding these features to all developers who might not need these new, really specialized features, and all you want to do is show a map with a marker and don't want all of our fancy new features. So we've added these libraries. So when you request the bootstrap, you ask for the particular libraries that you want. So in this example, the AdSense library, which has a component called the ad unit, which can render ads on your map. When this loads, that file, that AdSense module, or that AdSense library is then concatenated with the main interface library, main.js. It then extends the google.maps namespace to include AdSense.addUnit. So it's all still part of the same, download the same library. But we have not created a single additional download, and any developer who's not using this feature does not have any extra bytes added. I'm going to switch gears now a little bit and start talking about how you can use servers, both yours and ours and those around the world, to help you. And we're going to talk about caching here. So as just a little background to caching here, if a user is sitting in front of a web browser and asks for a particular website, and it's not in a cache anywhere, it will go all the way up to the original server to fetch the resources. Say maps.google.com, our cloud up at the top of the image. But subsequent requests, if the cache headers are set correctly, can be served by the browser cache, making the request almost instantaneous. That original request can take a long time if that server is far away or slow or lots of hops between the user and that server. But if there are all these intermediary caches between the browser and that end server. And so if a user, say, sitting next door, who's on the same ISP as our first user, loads that same page, when that user goes to request the page, it will go, say, to the ISP cache, because these people are on the same ISP, And most ISPs will have a cache sitting there that can serve these resources. And subsequent requests will also go to their own browser cache. Now, a third person who also maybe lives nearby, let's say these people are all in Australia, where loading things across the Pacific Ocean can be really slow, and it's great when things are hosted inside of Australia. This third user, also in Australia, but on a different ISP, when they request this page, they hit a content distribution network, something like Akamai, where these resources are cached within that resource. So that's within that server. So that's in Australia, instead of having to go all the way back up to the server. So by setting cache headers correctly, all users can benefit, not just the one who's loaded the page already. But you have to be aware. Say I collect photos of my favorite animal, and my favorite animal is a cow, and I'm going to use this cow to illustrate a point of having multiple resources on a page that need to be kept in sync. So I'm going to take my cow, and I'm actually going to split them into two, and I'm going to call my photo animal left and animal right, because this is a page dedicated to my favorite animal at the time. So I've got my cow, and I've split him in half into two parts. Now, I probably wouldn't actually split my cow image in half. I'm just showing you synchronized resources here. So it's important that the left half of the animal and the right half of the animal are always the cow. But then I take the strip to Nepal, and I see this really cool yak, and the yak is now my favorite animal. So I've decided to take my page and just change the file, the animal left and animal right file, in order to show the yak now. But say that when my user sits down, they go to load animal left and animal right. And because you can only control how long a cache is allowed to keep something in its cache, you cannot control when that it will keep it there. The cache is allowed to evict anything from it whenever it wants. So when the user goes to load the favorite animal page, when they load animal left, it's hit the cache, and the cow is still in cache. So animal left is the cow. But animal right has been evicted from the cache, and so the user's request goes all the way back up to the end server, and they get a yak. So now they see half a yak and half a cow. Not so good. So when you want to keep multiple resources in sync, it's important to use some sort of versioning. So here, if I just, instead of overwriting the animal left and animal right files, I'd rename them to yak left and yak right. Then when the page loads, when that HTML page loads that has these embedded, you have to change that page to say yak left and yak right. And then if that page was in cache, the cow will still be fetched. If the page was not in cache, the yak will be fetched. And we never get the yak-cow problem. So a good general rule for how to set cache headers, which are set on the server, so either your Apache server, App Engine, whatever your server is, a good general rule is things like HTML, don't cache them, or set their cache expiry to be however long of latency you want your pages to upload or to refresh. So if it's okay for users to see data an hour that's stale, let them be cached for an hour. But generally, don't cache HTML. Do cache forever JavaScript, images, CSS, all of that, and then use versioning within your HTML to fetch the new resource, and always get it from the server when you want it to be refreshed. And so you set the cache control headers to public and with an expiry date really far in the future. Now, I mentioned that the proximity of servers makes a big difference to the users. One way to help move things closer to your users may be to use a content distribution network, such as the Google Libraries API. The Google Libraries API makes some common JavaScript libraries available on Google servers, which are often going to be closer to your user than your server, just because Google has servers all over the world. So here in this image, we see that the user is the red star, and instead of having to go all the way to the yellow pentagon, which is your server, it only has to go to Google server, which is just a little hop across that channel of water.
All right. So now we've talked about some of the techniques to get the page and everything on your page loading quickly. We now sort of want to change pace a bit and talk about how to make the page itself, once it's in the browser, seem performant. So I'm going to start with a little bit of a walk down memory lane. In the beginning, back in 2005, maps.google.com was born. And with it came what I think is a pretty attractive marker that the designers came up with to really show locations on the map, where restaurants are, where pizza is, more importantly. To make it really stand out of the map, make it feel like it was actually standing on the map instead of part of it, they introduced a drop shadow, which made it really, feel like it was standing up, almost three-dimensional. The problem was, if a second marker was placed close by, that shadow from the first marker would obscure it, and you can see, it just looks terrible. So to get around that, what we needed to do was split the red marker image from its shadow into two separate images so that we could arrange them correctly. And now we don't have that problem. Another problem that we needed to solve was, how do you display more information about that point when the user interacts with it? So the info window was born. And the info window really takes that curved 3D look of the marker to the next level. It really pops out of the page, and it's got massive shadow behind it to make it feel like, a giant speech bubble popping out of the earth. The problem with that shadow is, though, it can obscure other things like markers nearby. And so you as a user, you can see that marker, and you expect, if I click that marker, its info window is going to open up instead. But the browser has a completely different interpretation of what's going on. It says that info window and that shadow, they're in front of that marker. And it only cares about what order images or DOM elements are arranged in the document. And so when you click the marker, it thinks you're actually clicking the shadow. To get around this, we actually had to add a third DOM element onto the page. And that was just something the user couldn't see, an invisible element in front of the marker, so that when the user did click it, that invisible element caught the click and was able to redirect it appropriately. All of that actually can lead to some performance issues. So on this map, I'm going to draw approximately 1,200 markers, which represent the location of Canadian airports. Susannah, will you do the honors?
Yes. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4.
Maybe 3.5 Mississippis? So it takes a long time to render those on the map. But what's worse is, even when they're on there, the performance is pretty terrible. You can see it's laggy. When I zoom, it just feels messy. It feels like I'm not interacting with the map anymore. It's just a kludgy experience. So as an API team, we really had to solve this problem. And there were two ways we really could do it. One was to simplify, to get rid of this marker, which we've all come to know and love. Try and simplify it, maybe make it smaller and boxier, get rid of shadow so we didn't have any of these clicking problems. Maybe simplify the info window again, make it smaller and boxier, and then just use normal DOM rendering. Or we had to work out, how do we solve this problem while keeping the aesthetics? And the lesson we came to, well, what we learned was the DOM is slow. Every time your JavaScript reaches out and talks to that page and tries to make it do something, add an extra element, you are incurring a real cost. So that's why we were really excited when Canvas came on the scene. Now, for those of you who aren't familiar with Canvas, it's considered one of the HTML5 technologies. You basically can think of Canvas as your favorite paint program. It's just a dumb pixel buffer that sits on the page. You can draw points on it, you can draw lines and circles, you can write text into it, you can even draw other images into it. But once you've drawn those things, the canvas doesn't care about the content anymore, it just worries about the pixels, so what it looks like. Just to give you an idea of how quickly Canvas performs compared to images, I'm going to draw 10,000 images here on the left. You can see it's not quite 3.5 Mississippis here, but it's still noticeably slow. You can see the delay. If I do the same operation in Canvas, by the time I finish clicking, the markers have all been drawn. Now I'm just going to throw up a couple of code snippets, and these are just to give you an idea of what's involved in using Canvas. It's probably not something that you're going to use in every element of your page. It's really something where you're worried about performance. But here's what the code would look like, well, did look like in that left-hand side where I was using image elements. It basically consists of two things. One is creating a DOM element, which is the image, and setting its source and its position so that it's in the right place on the page and looks right, and then adding that to a parent node so that it's actually added to the document. The equivalent piece of code for Canvas has a couple of extra complications. One is, once we've got the Canvas DOM node, we actually have to ask the Canvas for its drawing context. So you can think of that as that dumb pixel buffer. The other thing we have to do is load the image onto the page and wait for the image to have arrived before we try and draw it into the canvas. As I mentioned earlier, well, I've been mentioning it a few times now, the canvas is just a pixel buffer. So if you try and draw an image that hasn't even arrived on the page yet, it's not going to know what to do, and it's going to just ignore it for you. Nothing's going to happen. So you do have to have that complication of waiting for an image to load before you can draw it. But you can see it's actually not significantly more code, just a little bit of a mind shift. So when we applied this and a few other little techniques we had up our sleeves to markers, you can see what difference it made. Susannah?
Okay. One Mississippi.
Oh. It's less than a Mississippi. It's probably a small creek somewhere. But now, as well as drawing quickly, look how that feels. It's panning smoothly. It's zooming smoothly. It actually feels like, once again, I'm in the page with the map. There's nothing between me and the map, and we're interacting directly.
One thing that should be noted, too, is this is actually a very fast machine that we're on here. And if you were on a slower machine, a smaller one, anything, that 3.5 Mississippis could be a lot more than that, and dragging would be absolutely impossible. Now, there's another part to how we made the markers as fast as we did with Canvas. And this is to talk, and I need to back up a little bit to talk about and explain how we did this. So one of the initial features that set Google Maps apart from its predecessors originally back in 2004, 2005, was that it was infinitely draggable. That previously, maps had been loaded with one static image that had to change each time you wanted to pan to a new part of the map and load a fresh image. And this is partly because showing at zoom level 10, which is half of the zoom levels that we have on Google Maps, would take about 15 gigabytes of data to render that whole map of the world. So if you wanted a draggable map for the whole world at zoom level 10, your browser would have been able to do that. Now, we've seen that the browser can't even handle 10,000 small marker elements. And sure, 10,000 elements is different than one big one, but really it can't do either. So Google Maps, what it originally did was take that world imagery and pre-compute, cut it into slices, 256 by 256 pixel images that could then be sent to the client and stitched together there, which then, when dragged, would load as they're necessary and create this infinite dragging. So here we see in the center, that's the map that the user actually sees. And what's behind it is what we're not loading. Often we load a padding around it, but what's behind there would be what you would have to load in order to have the same functionality without tiles. So we apply this technique to a number of different things that we do on the map. One of those being those canvas markers. And so instead of just rendering all of the markers in the canvas all the time and having to have one that's as big as the map, we split it into these tiles and render them in parts. So when looking at the Canadian airports, if you're zoomed in on British Columbia, we will not render the canvas markers for all of the airports in Nova Scotia as well. We will only be rendering those for British Columbia, doing as little work as possible. Now, an alternative to using canvas markers and doing that all on the client is KML. KML is an open source format for representing geographic data and presenting geographic data. It's an XML format that allows you to specify place marks, extended information about place marks, polylines, polygons, ground overlays, and other things to render on the map. Now, we have in the Maps API a KML layer. And when you specify a KML file to that KML layer, it sends a request to our server, which goes out and fetches your KML file. So it must be hosted on a publicly available server. It fetches that KML file, comes back to the server, renders all of that parses that file and renders it all into image tiles that are then requested by the client. So each of these KML files are split into tiles, just like our marker rendering for the canvas, and just like our image tiles for actually showing the map. This means that you can show 10,000 or so place marks in exactly the same amount of time as one. There is no added cost to showing more place marks when loading it from KML. But KML is as I said, it's this XML format, and each time you want to change the data, you have to regenerate the file. So if you're trying to add more data, you have to regenerate the file, re-upload it, and of course version it because of caching. So an alternative to this is to use Fusion Tables. Fusion Tables is Google's online data store for any data, but it's particularly good for location-based data. Fusion Tables allows you to store in rows and columns any sort of structured data, and then to be queried by our Fusion Tables layer, either as an entire table. So here we see again the Canadian airports loaded. That's the entire table. It's all 1,200 airports. You can also specify a query to only fetch part of the table. This is an SQL-like query, and here Dave is showing if you specify, you ask for only airports with a minimum elevation. And so dynamically, we have changed this table, and at each level, it has fetched new tiles to show this airport data. So just like KML, just like our markers, we render these things into tiles so that many points to render take the same amount of time as a few points to render. Now, the other thing that both KML and Fusion Tables do, oh, and I should mention, there was a talk on Fusion Tables yesterday, so if you're interested in learning more, you should check out Catherine and James's talk online. The other thing that KML and Fusion Tables do is they wait until a user needs that extended data before loading it into the client. So if you were to render those, all those Canadian airports by creating new markers and having us render them, though it may be fast and draggable, you would need to have data at that time to show what you want in, say, the info window when you click on it. But with KML and Fusion Tables, when Dave clicks on that marker, at that time, we go off to the server and request the extended data for that airport in Nunavut. And so no extra data has been loaded into the client until it's required. Now, you can tile anything. You can do this yourself. At the time of the floods in Brisbane in January, we put together a map, and we had this great overlay that showed where the flood levels, where the river levels were predicted to go. But this image was quite large, and loading it in took some time. And again, this is a fast machine, so it didn't take as long as it would have on many other machines. But dragging the map became nearly impossible. And this file is, Dave, how big is this file?
Just over 2 megs.
2 megs. And so that makes it almost impossible for the browser to render. And if we zoom in further, it will become worse and worse. So instead, we need to create tiles. Now, the ImageMapType class in the Maps API makes it very easy to load tiles. You can use open source tools such as MapTiler and a few others to cut your large image into individual tiles. What this does is, at each zoom level, creates tiles at the specified for each coordinate in whatever size images you're telling it. So we often use 256 by 256 pixels. It works pretty well. So after cutting the large image into these individual tiles, the ImageMapType defines the getTileURL function, which just returns a URL to the image that you want. And so for our format, it's the path for where all the tiles are, and then they're stored in one directory for the zoom level, and then in each zoom level, one directory for each x coordinate, and then each y coordinate. You can have your format be whatever you want for these, but all you need to do in the ImageMapType is return the URL for the image for the coordinate and zoom level that we've passed in to getTileURL. So the result of that, it loads a lot faster, it zooms, or it pans, it zooms, and we get the added benefit that ImageMapType supports opacity, so we no longer have an opaque blue overlay on the map. we now have this semi-transparent blue, and you can still see where the towns are that were to be flooded. You can tile anything, not just images. The MapType interface in the API it gives you a coordinate, and you create a div, and you return the div instead of a URL. So here I've created this coordinate map type, which, so for each coordinate and zoom level, it just prints out the coordinates, which could be useful maybe to use while developing your other tiled map types. So the map type interface just requires you to specify a tile size and to define getTile. And so getTile passes in the coordinate, the zoom level, and the document. We pass in the document so that we don't have any problems with iframes, so that we're sure that you are creating the element with the correct document. So you take our document, you call create element on it, make it a div. I guess you could give it any node. We'll attach any DOM element to the DOM for you. And then you can put whatever you want in it. And we will position it on the correct tile, because the world is split into these fixed boundaries, where at zoom level 0, there's one tile, and so the coordinate is always 0, 0. It's then at zoom level 1 divided into quadrants, and then at each tile from there is divided again into 4.
So the other approach you can take is simplifying the data before you give it to the browser, because as we saw, everything you give to the browser incurs a cost. If you saw Jez and Luke's talk on user experience yesterday, then you also realized that often bombarding users with information can overwhelm them. It's the same with the browser. So the principle you should always apply is keep it simple, Susannah. Thank you. I practiced that one earlier. Here you can see we're using the open source marker clusterer to again use those 1,200 Canadian airports on the map. But instead of rendering 1,200 markers, we're rendering relatively few, which just give you an overview of where those airports are. So here, the heavy lifting was done by the JavaScript before we started talking to the DOM. And doing things in pure JavaScript is generally really quick. Now, things like JavaScript and Canvas, as we saw, can really start to take away that heavy lifting from the browser. But a new technology which takes it one step further and actually asks your user's graphics card to take away the heavy lifting is WebGL. WebGL is based on the OpenGL ES library, which is the same graphics libraries used by all mobile devices to render graphics in 3D context. So it is like a powerful open standard to get 3D graphics performance. To give you an example of how powerful this can be, I've got two panoramas, street view panoramas here, which I've rendered in two different ways. On the left-hand side, I've rendered using just traditional Canvas 2D, and we've carved up the street view imagery into triangles to make it actually fit together right, so you get the right perspective. And you can see, as I pan, it's a bit jumpy, it's a bit jarry. It's not terrible, but again, it's not great. And actually, we had this this same demo running on my Mac, and it was absolutely unusable. You'd get a refresh maybe once every second or so. You couldn't use this at all. So if you do check out our slides later online, try it out on your own machine and see how Canvas is performing for you. On the right, we've got the same imagery, but this time using WebGL, so we're using the graphics card. And you can see it's absolutely smooth, it's absolutely crisp. And that's because now the browser's not doing the work, it's the graphics card. And this is sort of the exciting future that we're getting towards in browsers, where we can rely on these tools more and more to actually do some of this heavy lifting and get a much more compelling experience for our users. All right, so to get started, here's some great resources. I recommend you go and check out all three. The top one's really how do you get your website and your server working well, and the compiler's about that JavaScript compiler I talked to earlier. And then, of course, I really encourage you to go and check out all our API documentation, which includes a lot of guides, articles, and example code as well. So thank you all for your time, and we'd love to answer any questions you've got if you want to stand up to the mic.
Hello, I've got two questions, if that's okay.
Sure.
The first one is, when you're rendering the KML tiles and you're rendering things from Fusion tables, how much do you depend on the pure raw power of the cloud to dynamically render those tiles? And how much do you render that kind of ahead of time? So if a user uploads data to Fusion tiles, or to the Fusion tables, do you try and do a couple of zoom levels? Because there's 23, you don't want to try and do everything.
Actually, usually we rely on the pure raw power, especially with Fusion tables, where we don't know what query and what, even what the data might be in the table until you ask for the tile. So we really have to do all of that rendering right there and then. We do some smart things like trying to index it, but it's mostly just power.
Okay. And
it's
the second,
also, it has to make a round trip to the server to actually fetch the tile, which is probably so much greater than the amount of time we're spending on the server, that it's so greatly outweighed by the network time.
Okay. And the other quick question I had was, a lot of this is great, but there's a lot of customers, larger enterprise or disconnected networks that may want to use this or don't want to be uploading their data to public Google servers. Is there any way that this will be integrated back with like the Google Earth Enterprise team, bring some of this capability back that way, especially the KML rendering?
I'm not sure of any plans on those regards. Definitely all the stuff we talked earlier, like the canvas, you can use that without ever the data coming to us. And there is also, there isn't Premiere offering for Fusion tables. You do store the data in the cloud, but it does help you keep it much more private when it comes to map rendering.
Okay.
Yeah.
This is also a great time to pitch at 12:45, I think it is. We have the Geo Fireside chat where we'll have a number of our product managers who would be even better to answer such questions.
Okay, thank you.
Regarding the using Canvas for drawing the markers, does it fall back to the old style of rendering them if the browser doesn't support it?
Yep, we fall back whenever the browser's going to use the old way better. And also for things like draggable markers, it's more complicated to do that in Canvas than it is to have a DOM element there. So there's a number of reasons we fall back when we need to.
Okay, thank you.
We also, we used VML for IE, but it turned out VML wasn't actually doing the same techniques as Canvas, as doing it in VML wasn't actually such a win. So we're still rendering DOM elements there, but doing some other sort of trickery to get it to be as fast as possible. But so it's important to look at what you can do in Canvas, you can normally do in VML, but it's important to figure out, are you actually winning from doing it in VML?
Yeah, and maybe on that, can you elaborate which browsers might not support Canvas or VML, if you know?
Right. So Canvas is supported in all WebKit browsers.
On Mozilla, modern Mozilla.
Yeah.
And IE9, I think. Is that right?
Yeah, I think so.
Yeah.
And we've found it to be faster on all of those browsers.
Any news on supporting vector type of drawing, such as a SVG type of drawing, instead of just a raster caching?
It's a really exciting problem. We don't actually have any concrete plans, mostly because still, like as we saw with WebGL, it's the browsers that are catching up. We could probably do that all in native client, as you see in the Maps client on Android. But then doing it in the browser is just that much. We're just one step behind.
All right, thanks.
And you mentioned SVG. It's a good time to mention Android doesn't actually support SVG. So if you're doing something in SVG, make sure you have a Canvas implementation as well.
Thanks.
When you use the canvas to draw the markers, you can't attach the click handler directly to the marker. So
Right.
there's magic done by Google Maps in the background to figure out where it actually goes?
Yeah, exactly. And we find that's not slow. Because you're only clicking very rarely, you can spend a few tens of milliseconds then going back and working out which point corresponds to which marker, and the user doesn't notice.
But that just all happens locally in JavaScript, right?
Yep, that's right. Yep.
Something, though, in Canvas, anytime that a resource is loaded cross-domain, you can't access that pixel data any longer. So one way to do hit detection with Canvas is to inspect the pixel data of the canvas and see whether there's something there or not. But if you've loaded your image cross-domain, you can no longer do that for security reasons. So you need to have another way. And so this is a problem we face because the API is always loaded on your domains, and we're fetching images from our domain. And so we can't use that sort of hit detection. We have to actually keep track of where everything is that we've drawn, if that makes sense.
Any suggestions about improved performance of multiple polygons in a map? A large number of polygons?
So we certainly have spent a lot of time making a lot of small polygons fast and few big polygons fast. I think there were some recent improvements in the last month for polygons. So if you have a site, I would say the best thing to do, if you have a site where you think your polygons are just too slow, send it to us.
And try the most current version first, because we have made a lot of improvements recently.
But that's something, one of the guys on our team is really into getting polygons to be fast. So if you send him a demo that shows that they're not fast, chances are he'll spend next weekend
And how do we send it to you?
The best thing to do is actually probably post it on the group.
Okay.
Because other people might be interested in seeing that as well. So do we need to tell you where our group is? Search for Google Groups Maps API v3.
If you go to the documentation, it's all linked from there.
Hi, you showed clustering a few slides ago.
Yep.
Is there any clustering done or can be done natively on mobiles?
That clustering was all done in JavaScript.
Yeah, that was Fluster, wasn't it?
No, it was the open source v3 marker clusterer, which is linked to from our documentation and the groups. And it's all done. Instead of giving the marker to the map, or the map to the marker like you usually would, you instead create the marker and give it to the clusterer. And then it worries about putting them together and forming those clusters all natively on the client.
And does that handle custom markers as well?
Yep, custom. Actually,
that was a custom
that had
marker.
Custom markers.
The little blue guy was a custom marker. So you just you create markers the same way you would anytime. So you pass it a full marker options object. And then the one thing you don't do is set the map on it. And you give it to the marker cluster, and it will render them.
Yeah, for an Android or an iPhone app, is it recommended to use a web view and then render the map inside the web view with a v3 API, or is it better to use a native?
So I'd say we're partial to the browser, since that's what we work on. But I'd say that the real benefits of using the browser are that it's cross-platform. You write it once for iPhone and Android. And we actually also work on BlackBerry and Bada. So you get 4 mobile OSs for one. And then we have much more active development with a lot more features. So you get a lot more.
Performance-wise, they are getting very close, native versus web view.
We're still slower.
Okay, and the second,
for what it's worth, correct me if I'm wrong, Luke, but the map that you've got in the I/O application on your Android uses WebView. Okay. Just to give you a feel of what the performance is like.
Yeah.
No, we have an app in the market. The second part of the question was using Street View DOMs in our app. We try to simulate walking down the streets, and we pick great routes around the world and let people sample them. So to simulate that, we load panoramas one after the other. And using V3, we don't really get that smoothness that we see in a Flash-based or any other in a browser-based. So are there any techniques or trickery there to try to make it like a seamless walk down the street using Street View?
It's certainly something we would like to provide for you in the future. We would like our implementation to be just like Flash. It may or may not get there. In any, no promises as to when. I don't know.
I think there is active interest in it in the Maps team generally. So I think you will see a lot of improvements coming.
Thank you.
Yeah, I can't think of some great techniques for you to do it on your own locally.
Okay, thanks.
Extending on the previous question about the overlay of the click handler, there's a nice example. You have a mouse pointer which changes when you move over a point. If you have a canvas, how do you do it if you have, for example, 10,000 points?
Again, we have to do it all in JavaScript wherever we can. So we know where the points are, and we basically go from this x coordinate. Does that correlate to one of the markers, and should we change cursor?
So with the tile, you also send the data to the client?
Oh, yes, for these ones, yeah. We send a little bit of data, just enough to let the browser know what is clickable, but not the entire information about what each airport is, for example.
Okay.
Yeah.
Going along with the two questions ago, regarding the web view with the map inside versus a native app.
Yep.
One thing that I really feel to be a limitation today is that the web view doesn't have pinch to zoom, and people feel like that they're entitled to this functionality and it's not available in WebView. Is this going to come sometime?
It's available on the iPhone, and it's available in Android 3.0. So if you try your tablet, it should work.
Cool. Okay.
And that was a limitation. It was not exposed in the browser by Android. So it would have worked. Our code works for it, but Android didn't, though it used pinch to zoom, it did not expose multi-touch events. Every touch event still only had one touch in it.
Great.
But Android 3.0 fixes that. And let us know if you have problems with that, because we don't have the tablet, so we haven't played with it as much as you will.
Hi.
Hi. For your Canvas example and Fusion Table example, following the click event, you create a info window, which is the information is populated by, it goes back to the Google server. That includes the extra round trip time. I assume that's quick, but I was just wondering what's your thoughts on that, if that.
Yeah, it's sort of weighing up the benefit of how much does it cost to get the page actually loaded and functional versus how much will the user wait. A lot of the time you can do tricky things, like if you notice the user hovering on it, then start, because even if they don't end up clicking, you really haven't wasted much. And yeah, I think also if you can, when you do know you have to go back to the server and fetch something, just let the user know that something's happening, because they'll get frustrated and click it 17 times before, you know. So it's sort of the combination of those two things, trying to pre-guess and also letting them know what's happening.
But that data is so simple that it's so small that it's okay. But if you knew your user was, or you knew you were going to show these info windows, then maybe don't load them when you first load your page. Do it in some timeout when you're done rendering everything else, and then fetch as many as you can together. Would be my tip for that.
Last question?
For the Fusion Table example, again with the click event, if you had multiple markers stacked on top of each other, could you receive all the information from all the markers with the click event?
I think the implementation at the moment just supports getting one event.
I mean, theoretically, not with Fusion Tables, but if you were to implement this, you could pick to have that feature. But that's not how we've done it.
Thank you.
Great. Thanks, everyone. And if you've got any more questions, we'll be outside afterwards.
And fireside chat in an hour here.